Yeah, this is an old video, the original video. So the picture is very bad, and the the sound is very bad as well. But I hope you could see how the hammer and the feather dropped exactly at the same time due to no air resistance on the moon. And now that you saw that, let's see another one which is more modern, and perhaps you know Brian Cox from documentaries, where there is a similar experiment taking place in a controlled environment. So let us see that.
They built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber. We dropped 2 millitorr in the last 30 minutes. But once it's complete, there's a near perfect vacuum inside. 6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop. 10, 9, 8, 7, 6, 5, 4, and it's on, 2, 1, release. Look at that. They came down exactly the same. Wow. Look. Exactly back outside. Exactly the same. Feathers don't move, nothing. That's just really Isaac Newton was saying that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all.
Right, guys. I hope you'll forget the last comment about Einstein, because we're not doing relativity here. We need to explain things using the Newtonian mechanics. So according to Newton's second law, there is a force acting on both the ball and the feathers, the force of gravity, and that is why they accelerate downwards, the feather and the ball. And in the absence of air resistance, the two are expected to fall at exactly the same time. And this is exactly what we see here. They fall at exactly the same time. Of course, when we saw the ball and the feathers falling, it was in a slow motion, because if we were to see it at real time, they would fall so quickly that we might lose a point. But it was so remarkable to see them both falling at exactly the same time. I hope you saw that clearly, and I hope you could hear the sound as well. All right, please tell me if there was a problem with the sound or did you see it clearly? There was no problem. Good, great. Okay, so now that we saw those two videos, I wanted you to see that in the absence of air resistance, how even these fluffy feathers can fall at exactly the same time as this very heavy ball, like the same way like the feather and the hammer fell on the moon at exactly the same time. All right, so now that we saw these documentaries to see that these things happen in real life, let us do some problems. Let us solve some problems as we usually do. This first picture here is about air resistance and terminal velocity. Now in the real world that we live, where there is a lot of air resistance, and this actually is the example, the picture that from your book on page 40, and I hope you see it clearly here. Let us discuss it a little bit to see what is the story between air resistance and weight. So they have now this guy who is supposed to be falling from an airplane, and which force acts on it initially when he's just coming out of the airplane? It is the weight, of course, the weight. All objects near the surface of the earth have a weight, and he starts falling with the weight acting on him. Initially, when its speed is still very small, because remember he starts falling from rest. We assume he falls from rest when he steps out of the door of the airplane. When his initial speed is small, there is a small air resistance acting on him. Remember that the air resistance is what we call the drag, due to the presence of the air, and acts in the opposite direction from where the motion of the object takes place. So if the motion is downwards, the air resistance acts upwards. And initially it's small, as you can see from this small arrow here. But as the guy falls faster and faster and faster, he accelerates downwards because there is a downwards overall force acting on him. As its speed increases, the air resistance also increases. And what is important to understand here is that the air resistance depends on the speed, on the magnitude of the velocity. Let's leave speed for the time being. Depends on the speed and on the area of the object. In this case, the area of the body of this guy who is falling. So it depends on the speed and on the area, the surface area of the object that is falling. So that is why as the speed increases, as the guy falling down, that is why the air resistance also increases. So the air resistance increases, and as it increases, comes a time where it becomes equal to the weight. And here is this case where we have this air resistance being equal to the weight, shown by these two arrows, which are in opposite direction and equal in length. So once those two arrows now become equal, the resultant force acting on this guy is zero, isn't it? F resultant here, F resultant is zero. And since it is the resultant force is zero, this guy now falls with constant velocity. That means that his velocity now is constant. We call this the terminal velocity. Terminal velocity. Let's call it terminal velocity 1, because this is a terminal velocity that this guy reaches when there's no parachute open yet. Just he reaches this velocity just by falling all alone. All right. Now this terminal velocity can be quite big. It could be about 190 to 100, up to 200 kilometers per hour, perhaps. Let's say 190 kilometers per hour. The truth is that this, how big this terminal velocity is depends on the height on the altitude from which this guy is falling, because if he falls from a very high altitude, the air is thinner. And if the air is thinner, the air resistance is smaller, so it can reach much bigger terminal velocities than the 190 kilometers per hour. But nevertheless, I have some notes here at the bottom. Roughly, about this terminal velocity can be reached after about 12 seconds after he drops from the plane. And the distance traveled during this time could be about 450 meters. But you see, all these numbers say about, because we don't know exactly which altitude this guy dropped. But nevertheless, these would be some characteristic values. Now, okay, although this velocity now will stay constant as this guy falls towards the Earth, I mean, if he falls on the ground at this velocity, there will be a lot of damage on him. So this is not a good velocity to fall and reach the ground. So that is the reason why we have a parachute. A parachute, which is something, an object that supplies a very large surface area. Because remember, the resistance depends not only on the speed, but also on the surface area of the object. So because now suddenly this large surface area appears due to the parachute, the air resistance increases drastically and very suddenly. So this is the new air resistance now, the new drag air resistance. And you see now that this air resistance is a force which is much bigger now than the weight. This is still the weight. The weight has not changed the magnitude, so it's shown with the same length of arrow. But the air resistance now has gone very big, and you see there is a resultant upward force here, because this is a much bigger force than the weight. So this would be the new resultant force. And because there is a resultant force, an upward resultant force, which is now opposite the direction of motion. Remember, this guy still drops downwards. So there is a force acting opposite to the direction of motion. Obviously, this guy is going to deaccelerate now. It's going to start slowing down. So it slows down until again, and of course, as he slows down, as his speed decreases, the air resistance will decrease as well, because remember, the speed, the air resistance depends on the speed. If the speed decreases, the air resistance decreases. So the air resistance will start decreasing, and eventually again it will come a place in time where the two forces will become equal again. So here is the air resistance now. It has come to the same size as the weight here. The weight and the air resistance become equal again, resistance. But now that they become equal again, means that this guy is going to drop again at a constant velocity, a new terminal velocity. Sorry. So let's call this terminal velocity 2, terminal velocity 2. And this velocity now has a new value. It's not the same as this one. It's a new value here, a smaller value. And usually a characteristic value of this new terminal velocity would be about 10 meters per second, says in your book, which is about 30-something, 35, 36 kilometers per hour. And of course, this is a much smaller velocity than the 190 kilometers per hour. So obviously now the guy stands more chances to make it safe and sound on the ground, especially if he knows how to land at this much smaller terminal velocity. So the reason of the parachute is to slow us down when we drop from a very high altitude until we reach a terminal velocity which is kind of safe for us to land safely. So what do we need to understand here is that the air resistance or drag changes as we drop. It changes as our velocity changes. The bigger our velocity or speed, the bigger our speed, the bigger the resistance. It increases as the speed increases, or it decreases as the speed decreases, until its size becomes equal to the weight, to our weight, to the weight of the object that drops, and then we reach a terminal velocity. And how can we make it? How can we manage to reach a terminal velocity which is small, which is safe to land? By increasing this area of the object that is falling, in this case by opening this parachute to decrease our velocity that we are dropping. Now, okay, for these terminal velocities and air resistance, guys, do you understand this part? Because air resistance appears in many problems because we have airplanes and parachutes, and I saw it. Any questions on this picture here, guys? If not, we can continue. Yeah, no. Good. All right. So you understand that the air resistance changes with the speed. Great. Yeah. All right, let's share again. Now let's see some problems where we have to add forces to find the resultant force. We'll start with some easy problems first. Here we have an object. We assume that this object is on some surface. On some surface, they don't show the surface, but nevertheless, there is some surface. And there are two forces acting on this object. One force acts to the right, and it's 80 newtons. The other acts to the left, and it's 45 newtons. We can add them, but okay, that's easy. I mean, you might say, hey, yeah, the resultant force here, the resultant force is 80 minus 45, 80 newtons minus 45 newtons is how much? 35 newtons. 35 newtons, and it's a positive number, which means it's to the right-hand side. But remember, and we must always remember that because we can slide forces, as long as we do not change the direction, we can also represent the same scenario with by sliding this 80 Newton force and having it appear like that. And the other one, which acts to the left, we can have it also like that. Maybe this is more understandable, perhaps, in order for us to subtract the two forces. So whether we subtract them in this representation or in this representation, it's exactly the same thing, all right? There is no difference between the two scenarios because we can slide the forces. All right. And frankly, I suggest that we use this second representation here, where the forces start from the object and move away, are shown as arrows moving away from the object, to help us understand more professional problems later on. All right. Let's see a more complex problem, like here, where we have three forces acting on this object. Again, we can slide the forces. Here we have our object. The 60 Newton force, I will show it there. And then we have two forces acting on the left. So here is the 40 Newtons, and here is the 50 Newtons. 50 Newton forces. So in order for us to find the resultant force, F resultant, what can we do? We subtract the ones that act to the left from the ones that act from the right. So what we can say 60 newtons, which is the one that acts to the left, to the right. Sorry, let's take, in all these problems, what I'm going to take to assume without even saying it is that to the right, I take to be the positive direction, which means that all forces that act to the right, I'll give them a positive value. like here I give it 60 Newton, plus 60 Newtons. And all the forces that act to the left, I will give them a negative value, okay? This being the negative direction. So 60 Newtons, okay, now I have to subtract the others that act to the left. Minus 40 Newtons, minus 50 Newtons. And I do the calculations here, and how much I have altogether. 60 minus 40 is is plus 20, minus 50 is minus 30, isn't it? Check my calculations, guys, because I don't trust in myself. Okay, minus 40, minus 50, minus 80. No, it's minus 20, yeah? Okay, something like that. Sorry, nonsense, goodness. Ridiculous. When I have a live lesson, I don't think. Minus 30. Okay, minus 30 Newtons. Which means that my resultant force, since I ended up with a negative sign here, means that my resultant force is actually 30 Newtons and acts to the left. It's in this direction, acts to the left. So there is my resultant force. It should look like that. An arrow acting to the left. And if I was to draw my arrows to scale, say that 1 centimeter corresponds to 10 Newtons, this should be 3 centimeters. If I was to draw it on scale, 1, 2, 3 centimeters. This would be 6 centimeters, 1, 2, 3, whatever. And we're done 1, 2, 3, 4, and 1, 2, 3, 4, 5. All right. So the moral of the story is that my resultant here, because I found the negative value, acts to the left, and it has the magnitude of 30 Newtons. In this example, we have like 4 forces acting. And we see that my forces now don't act all on the horizontal, but we have also on the vertical. So if I want to find my resultant, it's good to take the vertical separately and the horizontal separately. So let's call the vertical Y, for example, and on the vertical on the X. All right, so on the vertical, first of all, we have 2 forces acting. One is 40, one is 20. Let's say that whatever is up, I'll take it as positive, which means on the Y, on the vertical, I have 20, my resultant force is 20 Newtons minus the 40 Newtons, because the 40 acts downwards, and the 20 minus 40 is minus 20 Newtons, which means my resultant force on the vertical level is a force that has a magnitude of 20 Newtons and acts downwards. Now, on the horizontal level, what do I have on the horizontal? I have, again, 2 forces. One acts to the left, the other acts to the right, and they are equal and opposite in direction. So 20 Newtons minus 20 Newtons gives me 0, isn't it? Which means there's no horizontal force there's no force acting on the horizontal. The forces acting on the horizontal are balanced and give a resultant 0, or net force 0. So here my net force is 0. F resultant is 0. Okay, so I only have a resultant force on the vertical, which is 20 Newtons and acts downwards. Guys, is this okay? Do you follow here with vertical and horizontal forces? And yeah, okay. We don't have much time left, but okay, this one has. Let's do this one quickly. What do we have here? Again, we have horizontal and vertical forces. On the horizontal, again, we have 100 Newtons to the left and 100 to the right. Those two balance So the resultant force on the x level, on the x-axis, is 0. On the y-axis, what do we have on the y-axis? Resultant force on the y, we have 20 plus 40 up is 60. 20 plus 40 is 60 up. So we have 60 up, 60 newtons, and we have 100 newtons down. Now we have a resultant force here, which is 60 newtons minus 100 newtons. The resultant is minus 40 newtons, which means my resultant force is downwards, and it has a magnitude of 40 newtons. All right. So this is my resultant force in this case.